Hello there, and welcome to Science for Sleep. I'm really glad you found your way here. Maybe you're in bed, lights low, a blanket drawn up around you. Maybe you're just sitting in a quiet space trying to give your thoughts a place to land. Wherever you are, however you are, this little corner of the night is just for you. A gentle pause in the rush of things. A small, calm space where we can let big questions arrive slowly, without pressure, without answers that come too quickly. This isn't a lecture, it's not homework, just a conversation whispered through the dark. Tonight I want to talk about something older than time. Or maybe not older exactly, because time itself might not apply here. But you see, that's the thing. Before time, before space, before anything we can really name or picture, something else was, or wasn't, or might have been. Already the words start to fold in on themselves, don't they? But that's part of what makes this so interesting. You've probably heard about the Big Bang. It's the idea most people start with when they imagine the universe coming into being. A kind of explosion, though not really an explosion the way fireworks burst in the sky or engines fire. This one didn't happen in space, it created space. There was no centre, because it happened everywhere at once. No edges, because space itself was unfolding as it went. And time too. Not ticking before, not waiting to be counted. Time was born with the universe. It didn't lead into it. It emerged alongside everything else. So then, and here comes the question that draws us in, what came before that? It seems like such a simple thing to ask. We do it every day. What happened before lunch? What came before that song? What was here before this building? Our whole lives are wrapped around this idea of before, one thing then the next, a line of moments, each one giving way to the one after. But when we try to apply that to the beginning of everything, the line stumbles, it loses its footing. Because if time itself began at the Big Bang, then what came before isn't really a meaningful phrase, not in the way we're used to. Still, we ask, we wonder, we can't help it. It's like standing on a beach looking out at the ocean and asking what's past the horizon. Even if you know the map, even if you've seen the satellite view, there's still something about that wide stretch that makes the mind reach further. That's what this question does. It stretches you, not with stress or strain, but with a kind of quiet curiosity. I wonder, as you're listening to this now, what time is it where you are? Is it the end of your day, or the start of a night full of stars? Are you drifting towards sleep or just hoping for a little rest? Are there clocks ticking near you, or has time already begun to slow down a bit? I like to ask that because time feels different for each of us. Slower when we wait, faster when we laugh. Sometimes it drips like honey, other times it disappears like breath on a window pane, and yet we measure it like it's solid. A second, a minute, an hour. We set alarms, we write deadlines, we trust it to move forward. But what if forward didn't exist? What if time never started ticking at all? If you're already enjoying this moment as if it's giving you even a little bit of peace, it would mean a lot if you gently tapped like, or maybe subscribed, if you think you'd like more nights like this. And if you're listening from somewhere special, maybe a mountain cabin, a city high-rise, a long bus ride under a dim sky, I'd love to hear about it. I try to picture the map slowly lighting up with listeners, one soft dot at a time. A quiet constellation of people asking big questions from small spaces. This video, like all the ones here, is meant for rest, for gentle thought, for soft curiosity. It's not medical advice, not a replacement for therapy or anything clinical, just a calm place to wander together, a quiet invitation to let your mind wander, even if your body stays still. So, let's begin. Or maybe not begin exactly. Let's drift in. Close your eyes if that feels good. Let your breathing settle a little. Not forced, not deep, just easy. Let the noise of the day fall behind you, like leaves brushing against a closed window. And now, think about this. Before the Big Bang, before time, before particles or planets or even space itself, there may have been something or nothing. or something that doesn't quite fit into either word? Because even the idea of nothing is tricky. We imagine it as empty space, a black void, a blank page. But even that image includes space, includes the idea that something could be put there, could move through it, could be measured against it. But what if even space was missing? What if there was no place to put a thing, no distance to measure, no direction to point? And what if time wasn't ticking? Not slowly, not at all. No past to remember, no future to anticipate. Just is or isn't. It's hard to describe, isn't it? Hard to wrap the mind around something that has no shape, no sound, no duration. But maybe we don't have to define it. Maybe we can just feel the edge of it, the outline of the question, the warmth of not knowing, without the coldness of fear. Scientists have thought about this question for a long time, not always directly. For a long while we didn't even know the universe had a beginning. People imagined it as eternal, infinite in both directions, no start, no end. But in the last century evidence has slowly added up. The expansion of space, the cooling of background radiation, the distribution of elements, it all points back to a beginning, a moment, or something like a moment, when everything we know came into being, or began to. So then again, the question taps us on the shoulder. What about before? That word still slips in, doesn't it? Before, even though physicists will sometimes gently correct it. It's not that there was a before, they'll say, it's that time as we know it might not apply. Still we ask, still we reach. Because somewhere inside us, curiosity doesn't let go just because the map runs out. It keeps walking. Maybe you've felt that before, that tug to understand something just beyond reach. Not because it will change your day or fix a problem, just because the wondering feels alive. The question itself has weight, not heavy, just present. We'll keep walking too, slowly, no rush. Each step brings us a little closer to an idea, or at least closer to the feeling of being near one. What came before the Big Bang? It might not have a final answer. Not yet. But the journey through that question is full of places to pause, to listen, to float gently through the dark with just a few soft lights for company. It's strange, isn't it, to realise that some questions seem to ask more than they can ever answer. They arrive with an innocent shape, a few simple words, a familiar rhythm, and yet they open doors that lead into rooms we've never seen. What came before the Big Bang? It sounds like a child's question. Honest, direct, curious. And maybe that's why it lingers so powerfully. Because buried in its simplicity is a kind of gravity that pulls our thoughts deeper than we expect. Most of the questions we ask are about things inside the universe. Why do stars shine? What is gravity? How did life begin? These are questions with context. They exist within a framework. There's space, there's time, there's matter to study and compare. But this one, what came before, tries to lean outside that frame, to peer behind the curtain even when the stage itself might be the first thing that ever existed. To even begin answering it, you have to understand what kind of question it is. It's not like asking what happened last Tuesday, or what existed before your house was built. It's asking something that may not have a reference point. Something that might not have a when or a where. And still, somehow we understand what the question is trying to reach for. That's the paradox. It doesn't quite make sense, and yet it makes just enough sense to keep asking. When scientists talk about the beginning of the universe, they often talk about something called a singularity. That's the point, mathematically speaking, where all known laws break down, where our models of space and time stop giving useful answers. It's not that something magical happens there, or that we need a miracle to explain it. It's just that our tools, our physics, our equations, our measurements, weren't made for that kind of environment. It's like trying to describe the taste of colour or the shape of silence. The concepts don't quite overlap, and so, at the very first edge of time, our models reach their limit. They can take us back to a fraction of a second after the Big Bang. incredibly close to the beginning, but not before. That moment is called the Planck time, the smallest meaningful slice of time our current physics can describe. Anything before that? We just don't know. Not yet. But not knowing doesn't mean not thinking. It doesn't stop ideas from forming. Some scientists imagine that the universe as we know it emerged from a quantum fluctuation, a tiny, temporary blip in a field of potential, where particles pop into and out of existence all the time. That might sound wild, but we see those kinds of fluctuations at the smallest scales of physics. The vacuum of space, what we might casually call nothing, is never truly empty. It's full of brief, unpredictable activity. So maybe the universe began as one of those fluctuations. Maybe something tiny, smaller than tiny, flickered into being and didn't fade. Instead, it expanded. It inflated. It grew so rapidly and so vastly that what was once the size of a subatomic particle became the entirety of space. Maybe time was stitched into that expansion. Maybe what we call before is just the absence of that stitching, a place where the loom hadn't begun its work. Even that idea, though, brings us back to the same edge. If space and time emerged from a quantum event, then what caused the fluctuation? What allowed it to happen? Was there a canvas for it to occur on? And if not, how do we even describe it? It's like asking what's north of the North Pole. At some point, the question stops having meaning. Not because it's foolish, but because the coordinate system runs out. There is no further north once you've reached the top. Not because it's forbidden, but because it's undefined. But again, that doesn't quite satisfy us, does it? Even when the philosophers and the physicists and the cosmologists tell us the question might be ill-posed, we keep posing it. Something in us needs to ask. Something quiet and stubborn. There are also ideas that try to sidestep the problem entirely. Some suggest that the Big Bang wasn't the beginning at all. Not really. Maybe it was just one phase in a larger cycle. Maybe the universe expands and contracts over and over, endlessly repeating. In those models, there was something before, but it wasn't a blank void or a singularity. It was just an earlier universe collapsing in on itself. That collapse, called the Big Crunch in some theories, could have rebounded into the next expansion, what we call our universe now. These models are elegant, but they also require assumptions about how gravity and energy behave at extreme scales. They aren't proven, they're suggestions, patterns waiting for evidence. And then there are even stranger ideas. Some theories propose that our universe is just one of many, a single bubble in a vast cosmic foam. In that picture, universes are constantly budding off from some greater whole, like droplets forming in a pot of boiling water. What we call the Big Bang might just be the start of our bubble, not the beginning of everything. In that sense, before, the Big Bang could refer to the larger multiverse, a backdrop of potential from which individual universes emerge. But then again, we run into the same challenge. If the multiverse exists, where did it come from? What made it possible? What lies beyond that? It keeps going, doesn't it? Each answer leading to a new question, each edge revealing another layer of possibility. It's like walking through fog. You can only see a few steps ahead, but those steps are enough to keep moving, enough to stay curious. Maybe that's the quiet brilliance of a question like this. It doesn't require a definitive answer to be meaningful. It draws you into the act of thinking, of wondering, of holding multiple ideas in your mind and letting them settle without needing them to fight each other. This isn't a battle of theories. It's more like listening to a room full of voices, each with a slightly different story, and finding comfort in their overlap. And all the while the question remains, not aggressive, not demanding, just there, like a quiet presence at the edge of thought. What came before the Big Bang? We might never know for sure. But the journey into that question is rich with insight, with beauty, with strange, delicate clues. We might not have a final answer, but we have hints, patterns in the cosmic microwave background. the behaviour of particles in high-energy collisions, the structure of space on the larger scales. And we have imagination. Not in the fantastical sense, but in the thoughtful scientific sense. The ability to explore models, to test ideas, to refine them over time. Even if we can't reach before, we can still map the contours of what's possible, so we keep asking. And in the asking, something shifts. The question stops being about answers. It becomes about attention, about standing still in the presence of something vast and letting yourself feel small, not in a diminished way, but in an honest one, because we are small, and yet we are capable of asking about the beginning of everything. That capacity alone is remarkable. When we talk about nothing, we usually mean it as the absence of something. No sound, no objects, no light, no movement. But in physics, especially in the kind of physics that tries to touch the very beginning of the universe, nothing gets complicated, because nothing might not be empty at all. Try to imagine it. Not darkness, not silence, not a blank space with a waiting edge. Imagine the absence of space. No distance to travel, no coordinates to stand on, no directions, not even a place to float. Imagine no time, no ticking, no change, no before or after. A condition where those ideas haven't even been invented yet. That's already hard to picture. And it gets stranger, because even when physicists describe a vacuum, what they mean isn't truly empty. At the smallest scales, even empty space is alive with energy. It hums with tiny, unpredictable flickers, quantum fluctuations, that appear and vanish, borrow energy and return it, spark briefly into being, and then fade again. These aren't just poetic ideas. We've measured them. They're built into how we understand the fundamental nature of reality. So if we say the universe began from nothing, we have to be very clear what kind of nothing we mean. Was it the absence of particles, of energy, of time? Or was it a kind of vacuum filled with potential, where quantum fields quietly stirred, waiting for a fluctuation big enough to light the fuse? That idea, that the universe could emerge from a fluctuation in a vacuum, isn't science fiction. It's a serious proposal. Some models of quantum cosmology suggest that in a quantum vacuum, which is not nothing in the traditional sense, random fluctuations can create pockets of space-time. Most of them pop out of existence almost immediately, but one might expand rapidly, irreversibly. That expansion is what we might call a universe. In that view, the Big Bang wasn't a bang at all. It wasn't a pop or an explosion. It was a smooth, rapid inflation, a spreading of space itself. The sound of nothing, if you like metaphors, wasn't silence. It was expansion, a sudden change from no space to space, from no clock to time, and yet still the question waits just outside the frame. If the quantum vacuum gave rise to our universe, what gave rise to the vacuum? Was it always there? Is it eternal? Does it exist outside of time? These are the kinds of questions that don't have clear boundaries between science and philosophy, between what can be tested and what can only be described in carefully constructed math. Sometimes, even in the most precise scientific papers, you'll see terms like pre-geometry or pre-space. They're attempts to talk about a condition where even the structure of space-time hasn't yet formed. Imagine rules that govern the game, but no board to play on. No players, just the rules themselves, waiting. Or maybe not waiting, because that too implies time. When theories try to model this, they often use imaginary time or complex numbers or alternate topologies, tools that are hard to translate into everyday language. But underneath it all is the same question. Could the total energy of the universe be zero? Could positive energy, like matter, be balanced by negative energy, like gravity, in such a way that the net cost of making a universe is nothing? That idea has been suggested by multiple physicists, including Stephen Hawking and Lawrence Krauss. In those models, you don't need a cause in the way we usually think about causes. You don't need a prime mover. The universe might have emerged spontaneously, as a kind of symmetry breaking, a ripple in an energy field that didn't have a direction until that ripple gave it one. And if that's true, if the universe came from a kind of quantum nothing, then before the Big Bang might not be a meaningful concept at all. There might not have been anything to be before. No hidden world, no waiting place. Just a transition, a sudden shift from one condition to another. But it's still hard to accept that. Hard to sit with the idea that everything, stars, galaxies, thoughts, breath, could emerge from a state that doesn't resemble anything we've ever experienced. And yet, at the quantum level, we see strange things all the time. Particles that act like waves, matter that tunnels through barriers, entangled states that behave as if space doesn't exist between them. So maybe it's not that reality became strange at the beginning. Maybe it was always strange and only later became familiar. Familiar enough to walk through, to live in, to ask questions from. Still, the sound of nothing lingers. Not a roar, not silence, but something in between. A quiet instability, a readiness to become, like a blank page that isn't really blank. It's full of potential. Every pixel ready to light up, if only something starts the story. You don't have to solve the equation. You don't have to trace the energy field through imaginary dimensions. You can just sit with the idea that even nothing might be more complex than it seems. That the simplest thing to say, there was nothing, might be one of the hardest things to truly understand. And if nothing is unstable, then something is inevitable. Not because it was planned, not because it was wanted, but because possibility contains its own restlessness. Maybe the universe didn't need a push. Maybe it didn't need a designer or a trigger or a moment of divine timing. Maybe it was just waiting to fluctuate, to move, to stretch out and become something measurable. And once it did, once that first flicker took hold, time began. Space unfolded. The laws of physics took shape, and the story we now live in began to write itself, one frame after another, one moment after the next. There's something quietly powerful about the idea of a pause. We're so used to movement, to things happening, to time pushing forward without permission. Seconds turning into minutes, days passing like signs on a highway. But a pause, a true one, interrupts that rhythm. Not with force, but with stillness. It's not a stop. It's not an end. It's just a space where nothing seems to happen, and yet everything might. If the universe began with a bang, or something like one, what, if anything, came just before it? Maybe we're not meant to imagine it as an event or a scene, but as a kind of stillness, a waiting. Not the calm before a storm, which implies something brewing in the background, but more like the moment before breathing in. That microsecond when your lungs are empty, your muscles haven't moved yet, and even your thoughts go quiet. Nothing is happening. But everything is about to. It's tempting to imagine that the pre-Big Bang universe was full of potential. But potential is already a kind of something. It assumes structure. It assumes conditions that can be measured, even loosely. But the further we move back toward that origin point, the more those assumptions start to lose grip. There might not have been matter, or light, or direction. Not even space. Because space is a thing. It's measurable. Even when it's empty. It has geometry. It stretches. It curves. You can describe it in equations. But if the Big Bang created space, not just filled it, but caused it to exist in the first place, then whatever was before, it wouldn't have space at all. And without space, there's nowhere to go. Without time, there's no way to wait. You're left with something that doesn't behave like anything we can test. Still, we try to wrap language around it. Some theories describe it as a kind of pre-geometry, a stage where the laws of physics hadn't differentiated yet, where particles and forces and fields were all blurred together in a single symmetric state, perfectly balanced, motionless, like a ball perched exactly at the top of a hill, stable, but only until the smallest push breaks the symmetry and sets everything in motion. That symmetry breaking, the moment when uniformity fractures and gives way to diversity, might be what started the expansion. Not a burst, but a release. Something that had nowhere else to go but outward. The stillness didn't last, it couldn't. Or maybe it did from its own perspective. Maybe within that state nothing changed and nothing needed to. Maybe only from our perspective, looking back through the lens of time and space. Does it feel like a pause at all? And what if it wasn't the first one? Some cosmologists propose that the universe didn't start from nothing, but from a previous universe that collapsed. In that view, the Big Bang wasn't a beginning, it was a bounce. The end of one cycle folding into the start of another. If that's true, then the pause between them becomes even more interesting. It's not a singularity in the traditional sense, but a moment, or whatever you'd call something that isn't time-bound, where all of space contracts to a point, then rebounds. The idea of a cosmic bounce offers an appealing symmetry. Expansion, contraction, pause, and then it happens again. But this introduces its own puzzles. What mechanism makes the bounce possible? Can gravity reverse itself at extreme densities? Do the laws of physics bend in some way we haven't yet seen? We don't know, that's the honest answer. But we can imagine. And in imagining, we give shape to possibilities, even if we can't test them yet. Some versions of the bounce theory rely on quantum gravity, a still incomplete attempt to unify general relativity and quantum mechanics. Others explore string theory or loop quantum cosmology, which replace the idea of a singularity with a smooth transition point. Instead of a cliff, it's a curve. Instead of an edge, a bend. And right at that bend, a kind of stillness. That stillness isn't peaceful in the way we normally mean it. It's not soothing. It's not quiet in a warm, safe sense. It's quiet because nothing can move. Nothing can change. Not yet. There's no direction for change to go. There's no time for it to happen in. It's a pause in the deepest sense. In daily life, we're used to the idea that things move because something pushes them. A car accelerates when you press the gas. A ball rolls when you nudge it. But at the quantum level, and especially at the cosmic beginning, cause and effect don't behave the same way. Events can happen spontaneously. Virtual particles emerge, exist briefly, and disappear. Fluctuations arise without warning, without a push. So maybe the universe didn't need a push either. Maybe it was resting at a kind of tipping point, and the pause we imagine wasn't empty at all. Maybe it was full of tension, the kind of balance that can't last forever. Something had to change eventually, or what looked like eventually once time began. Of course, from inside time, that moment feels impossibly distant. We live in a world of ticking clocks, aging bodies, spinning planets. Everything has a sequence, so to talk about a pause before time is like trying to taste a colour. But that doesn't mean it can't exist. It just means our language isn't quite suited for it. Not yet. You might be wondering, why does this matter? If we can't experience that pause, if we can't test it or see it, why spend time trying to picture it? Because the shape of the beginning affects the shape of everything that follows. If the universe began with a violent, sharp event, then its structure would reflect that, a kind of cosmic scar. If it began with a smooth, quiet transition, the after effects would show up differently, in background radiation, in the curvature of space, in the way galaxies form and spread, and also simply because the question matters, not for utility but for meaning, because it's part of being human to wonder how all of this came to be, not just the stars and atoms but the very framework that lets stars and atoms exist. We may never see the pause directly, but we might detect its echo, a faint fingerprint in the patterns of the universe, a whisper from a moment when everything balanced on the edge of becoming. At some point, as we trace the universe back through time, everything that's familiar begins to unravel. Galaxies fade into clouds, stars shrink into particles, the rules of chemistry start to blur, then the rules of physics themselves. keep going, and even the concept of position, of where something is, starts to lose its meaning. And then, right there at the edge, just before everything stops making classical sense, you step into the quantum world. It's not a place, exactly. More like a scale, a level of reality so small, so strange, that the rules we're used to no longer apply. Here, things don't have definite locations. They don't follow clean paths. They exist in probabilities, in possibilities, in whispers. Quantum mechanics isn't a theory of confusion. It's a theory of precision. But it doesn't describe things as fixed objects with predictable futures. It describes fields and fluctuations, interactions and uncertainties. Instead of a particle being in one place or another, it can be in both, or neither, until something forces it to choose. That choosing, or what we call measurement, is where things crystallize into facts. But before that, it's all just tendencies, likelihoods, waves of potential. Now imagine, if you can, that this strange and unpredictable world wasn't just part of the universe, but the whole of it. No planets, no atoms, just a churning sea of quantum fields, humming with fluctuations that pop into and out of being, virtual particles appearing briefly then fading, energy shifting in tiny, unpredictable ways, nothing fixed, nothing solid. That's the kind of universe some models propose existed before what we call the Big Bang. Not a world made of matter and space, but a quantum foam. A restless nothing where even emptiness wasn't truly empty. This idea isn't just poetic language, it's grounded in real physics. Even the vacuum, the lowest possible energy state, is not quiet in quantum mechanics. It's full of activity, tiny fluctuations that never stop, even in the coldest, most isolated conditions we can create. These fluctuations are part of what give particles their masses. They're built into the equations, they've been measured. So if that's true, then it's possible, just possible, that the entire universe began as one of those fluctuations. A quantum blip that for some reason didn't fade like the others. It grew, expanded, crossed some threshold, some tipping point where inflation kicked in and stretched that tiny, improbable ripple into the vast cosmos we now inhabit. But of course, this raises another question. Why that fluctuation? Why did it survive when countless others didn't? Was it random? Was it inevitable? Or is there something about the nature of quantum mechanics that makes it not just likely, but certain that something like this would eventually happen? Some physicists point to the uncertainty principle, a fundamental feature of quantum theory. It says that certain pairs of properties, like position and momentum, can't both be precisely known at the same time. The more you pin down one, the fuzzier the other becomes. It's not a problem with our instruments. It's a basic part of how the universe works. From this principle arises a kind of restlessness, a rule that says even in the quietest vacuum, even in the absence of heat or light or matter, there's still movement, still possibility, still noise. And maybe, just maybe, that noise is enough. Enough to give rise to a universe, not by chance necessarily, but by the very nature of what quantum mechanics allows. There's a term sometimes used in these discussions, quantum tunneling. It refers to the ability of a particle to pass through a barrier it shouldn't, according to classical physics. It doesn't climb over the barrier, it doesn't break through, it just appears on the other side. Because in quantum terms, particles aren't really point-like dots. They're described by wave functions, and those waves can stretch past barriers. And sometimes, improbably but measurably, they get through. Apply that concept on a cosmic scale, and you start to see how strange beginnings might not require a classical cause. The universe could have tunneled into being, not from somewhere else, but from a state where it simply wasn't, to a state where it was. It's a hard idea to hold on to. We're used to things having reasons, triggers, origins that look like causes. But in the quantum world, things don't always need causes in the way we expect. Sometimes the math just says, this can happen. It's rare, but not forbidden. And given enough time, or whatever exists outside of time, rare things happen. This is where quantum cosmology comes in, a field of study that tries to describe the whole universe using the tools of quantum mechanics, not just particles inside space, but space itself as a quantum object, a wave function of the universe, a description of all possible configurations, all possible histories, all possible beginnings. These models are still in their early stages. They're speculative. They rely on untested ideas from quantum gravity and string theory and other unifying theories. But they offer a framework, a way to think about a beginning that doesn't need a spark, but just a whisper, a ripple in the right direction. Of course, none of this is easy to prove. We can't rewind the universe to its first flicker, but we can look for echoes, patterns in the cosmic microwave background, tiny differences in temperature and density that hint at what inflation might have looked like. Those patterns give us clues about the conditions right after the Big Bang, and maybe, just maybe, about what led up to it. And if those clues line up with the predictions of quantum models, then we get a little closer to understanding. Not a final answer, but a stronger whisper, because that's what quantum theory gives us. Whispers, not shouts. Possibilities, not declarations. It tells us what might happen, and with what likelihood, but never exactly when or why. And maybe that's appropriate. Maybe the beginning of the universe wasn't a bang or a flash or a thunderclap. Maybe it was a flicker, a pulse, a tremble in a quiet field that tipped everything else into motion. Not a sound you could hear, but a shift you could feel. If you were something that could feel, floating in a state where nothing had ever happened before. There's a word that gets used often in cosmology, and even more in everyday language, but it rarely means the same thing twice. That word is vacuum. To most of us it means emptiness, a space without air, a sealed jar with nothing inside, something blank. But in physics, especially at the scale where the universe begins to take shape, a vacuum is anything but empty. In classical terms, a vacuum is simply a region without matter. No atoms, no particles, no dust floating in the light. You might imagine deep space between galaxies, the quietest part of the cosmos, where no star shines and nothing seems to move. But even that space, far from planets and suns, is not truly empty. There are fields there, invisible but real, and they don't stay still. They can't. At the quantum level, every point in space is filled with energy, not because of particles that we can see or touch, but because of the fundamental nature of quantum fields. These fields stretch through space, everywhere, always active, and even in what we call the lowest energy state, the vacuum state, they don't turn off. They fluctuate, they tremble, they generate brief moments where particles and antiparticles appear together then vanish. These events happen constantly, endlessly and measurably. So when we say the early universe might have emerged from a vacuum, we're not talking about a clean, silent nothing. We're talking about a sea of activity, a vacuum that's full of motion, even if it looks still from a distance. This leads to one of the more subtle ideas in modern cosmology. The vacuum isn't just a backdrop. It's not just the stage. It's an actor in the play. The properties of the vacuum, its energy, its structure, can shape the way the universe evolves. They might even determine whether the universe expands, how fast it does, and whether it ever slows down. One version of this is known as false vacuum theory. In that model, the vacuum we live in right now might not be the lowest possible energy state. It might just be a local minimum, stable enough to last for billions of years, but not perfectly stable. Like a marble resting in a shallow dip on a hillside. From the marble's point of view, it's at rest. But if something nudged it just enough, it could roll into a deeper valley, into a true minimum. That new state would be radically different. with different laws of physics, different particles, maybe even different dimensions. If the universe ever transitioned into that true vacuum, it would change everything. Space itself would rearrange. Particles would lose their properties. Forces would act differently. Life, as we know it, would end instantly, not with fire or collapse, but with the rewriting of physical law. This isn't a certainty, or even a likely outcome based on what we know now, but it's part of the equations. It's one of the things the math quietly allows. But even without invoking catastrophic transitions, the vacuum plays a major role in how the universe began. In inflationary cosmology, a widely accepted model of the early universe, the expansion of space is driven by a kind of vacuum energy. For a brief moment, this energy caused the universe to grow at an exponential rate. Not just expand, but stretch, faster than the speed of light, creating space itself in the process. This inflationary vacuum wasn't just active, it was explosive in its consequences. It didn't explode outward from a point. It didn't send debris flying. It expanded everything. Every part of space grew, not because it was pushed, but because the vacuum itself had energy, and that energy drove expansion. And then, when that vacuum energy decayed, when the inflation field fell into a lower energy state, it released an enormous amount of energy in the form of particles and radiation. That moment is often called reheating, and it marks the start of the hot, dense phase we associate with the Big Bang. In that sense, the Big Bang wasn't the beginning of everything. It was the end of inflation, the moment when the vacuum settled into the state we now inhabit, the moment when the energy that had been stretching space turned into the stuff we can measure, photons, quarks, electrons. But even now, long after that reheating, long after galaxies and stars and planets have formed, the vacuum hasn't gone quiet. There's still a residual energy, sometimes called dark energy, that seems to be pushing the universe apart. Not with a force exactly, but with the property of the vacuum itself. The same thing that may have triggered inflation is, in a different form, accelerating the expansion of space once again. This energy isn't something we can hold. It's not like wind or pressure. It doesn't come from particles moving or fields being excited. It's part of space. It's baked into the structure of the vacuum. And it's astonishingly small, so small that it took billions of years for its effect to become visible. But now that galaxies are far apart, now that gravity isn't strong enough to hold them together on the larger scales, we can see it. The universe is accelerating, not slowing, not coasting, but stretching faster again. And all of this somehow comes from a vacuum that's never truly empty. It makes you wonder what we mean by nothing at all. If even the quietest state of space contains energy, if even nothing can fluctuate, create, drive expansion, then maybe nothingness is just a placeholder for a kind of hidden activity. Not an absence, but a quiet fullness. A backdrop that is always humming. This idea isn't just theory, it has practical effects. The Casimir effect, for example, is a real, measured force that arises from the vacuum between two metal plates. Not from air pressure or heat, but from changes in the quantum field between them. Empty space produces a force. That's not intuition. That's observation. So when we ask what the universe came from and someone says the vacuum, they're not being evasive. They're describing something real, something strange, something we can't see directly, but something that acts, that influences, that might have started it all. And if that's true, then the beginning of everything didn't come from nothing in the way we think. It came from a vacuum that wasn't empty, a place, or maybe not a place, that contained the potential for motion, the seeds of time, the ingredients for matter, before any of those things existed in the forms we know. That vacuum didn't look like a sky. It didn't have direction. It didn't glow. But it moved, or allowed movement. And from that movement the first moments arrived. Expansion began. Particles formed. Light emerged. And here you are, lying quietly, breathing, wondering where it all came from. listening to the faint echoes of a time when space itself was being written, not by force, but by the energy of the vacuum gently stretching out into something more. At some point, the question shifts from what was there before to something even stranger. What if before doesn't exist? That might sound like wordplay or a trick of grammar, but it's actually a serious possibility in modern physics. If time itself began with the universe, then anything that came before it might not be a meaningful idea. Not because it's wrong, but because the entire structure that allows for before, clocks, sequences, change, simply wasn't in place yet. But how do you imagine that? How do you picture a state without time? Most of our thoughts are wrapped in it. Our memories, our plans, even our simplest perceptions depend on the idea that one thing comes after another. Time feels natural because we move through it. We measure it. We notice when it speeds up, when it slows down. We describe our lives in terms of it. Yesterday, today, tomorrow. But timelessness, what does that feel like? Try this. Imagine freezing a moment. Not in the way a photograph captures an image, but in a deeper way. No ticking, no heartbeat, no mental narration, no next. Imagine that everything that could happen is already there, but none of it unfolds. Not yet, not ever. Just a whole, complete, unmoving state. Now imagine that state isn't just still, but doesn't even contain the idea of motion. There are no hidden steps, no waiting, just existence, suspended. That's closer to what physicists mean when they talk about timelessness before the Big Bang. Not a frozen moment in a film strip, but a condition without film, without sequence, without running time. It's deeply unfamiliar. But it shows up in real models of the early universe. Stephen Hawking, for instance, once proposed that the beginning of the universe might not have been a sharp starting point. Instead of time emerging from nothing, he imagined a model where time, at the earlier stages, behaves more like a spatial dimension. In that model, the universe didn't begin with a bang. It curved into being. No boundary, no edge, just a smooth transition from timelessness into time, like turning a corner, not hitting a wall. This is sometimes called the no-boundary proposal. It uses imaginary time, a mathematical construct, to describe conditions where normal time hasn't started yet. It sounds abstract, and it is, but it offers a possible way to describe a beginning that doesn't have a singularity. No infinite density, no break, just a gentle rise from something timeless into something evolving. In that view, the universe didn't begin from nothing. It began from a state that didn't include time, and then transitioned into one that does. You might ask, what makes that different from nothing? If there's no time, no space, no motion, no change, how is it anything at all? And the honest answer is, we don't fully know. But some models suggest that even in a timeless state, the seeds of the universe could still exist. Not as events waiting to happen, but as possibilities, suspended in a kind of mathematical structure. A wave function that includes all possible configurations of the universe, but without any evolution between them, yet. It's a different kind of existence, not one we experience directly, but one that could, under the right conditions, give rise to the unfolding we now call time. To understand this better, think of a book, a physical one. All the pages are there right now. From the first word to the last, they all exist at once. But the story only happens as you turn the pages. The structure is static, but your reading creates a flow. Now imagine that the universe, at the very beginning, was something like that book. All possible configurations written into a timeless whole. And only when a particular path was taken, when a particular history began to unfold, did time emerge. Not from outside, but from within. In quantum cosmology, this is more than metaphor. Some equations describe the universe as a static object, one where time doesn't exist at the most fundamental level. But when you include an observer, or a particular configuration of matter, time begins to emerge. It's not fundamental, it's relational, a side effect of how parts of the universe interact. In that sense, time isn't a thing that always existed. It's something that arises, like temperature, like pressure. You don't find temperature in a single atom, but in a group of atoms moving together, temperature becomes meaningful. So maybe time is like that too. It's not built into the universe in the way we imagine. It's something that emerges when things start changing in relation to each other. And before that, there's a state that doesn't need clocks, doesn't need cause and effect, doesn't even need motion. This might sound like philosophy, but it's being explored seriously in physics. Equations like the Wheeler-DeWitt equation, a version of the Schrödinger equation applied to the universe, don't include time at all. They describe the universe as a whole, timeless entity. Only when you look at specific parts, or impose a kind of perspective, does time show up. This doesn't mean time is an illusion. It means that what we call time might be a higher level feature, not a basic ingredient, but a result of how the ingredients interact. And if that's true, then before time began, the universe may have existed in a kind of stillness. Not as a blank canvas, but as a complete picture that hadn't yet been revealed. Not in potential, not in progress, but in a form we don't yet have language for. Even now, this idea echoes through certain areas of theoretical physics, like string theory and loop quantum gravity, which attempt to describe space and time not as fundamental, but as emergent. As things that arise from deeper, more abstract structures. In those models, the early universe, the part we call before, isn't something you'd recognise. There are no frames of reference, no dimensions as we understand them, just a network or a field or a geometry that contains everything, but hasn't yet started to tell the story. And then something changes. A symmetry breaks, a configuration tips, a fluctuation reaches a critical point, and suddenly, not gradually, time begins. The story starts. The pages begin to turn. That moment, when timelessness gives way to time, is still hidden from us. We don't know what caused it, or if cause is even the right word, but from that moment forward, things begin to evolve. Space stretches, energy forms. The first seconds tick by, even if nothing is there yet to notice. You can't imagine timelessness directly. Not really. But maybe you can get close. Maybe you can feel what it's like to sit quietly, without thinking about what comes next. To rest in a moment that doesn't pull you forward. Not a frozen second, but a stillness with no push. A breath without the need to breathe. That's what the earliest universe might have felt like, if feeling existed at all. Not dark, not bright, not silent, just still. Waiting, not in time, but in form. And then, whatever then means, time began. And the moment you're in now started its journey toward you. At some point the question becomes, where does time actually begin? Not in the poetic sense, not as a metaphor, but as a physical boundary. Is there a line you can point to? A limit where time simply wasn't yet? In everyday life, time feels like a constant. We rarely think about it starting or stopping. We measure it. We use it. We feel it pass, but we don't question whether it has a beginning. It's just there, flowing, steady, reliable. But when physicists trace the history of the universe backwards, from galaxies to stars to atoms to the earliest radiation, they eventually reach a point where our current understanding stops working. That point is unimaginably small and dense, a place where all known laws of physics collapse into what's called a singularity. It's not that something dramatic happens at the singularity. It's that our math no longer applies. It breaks. It gives us infinities where there should be numbers, uncertainty where there should be prediction. This singularity isn't just a limit in space, it's a limit in time. According to Einstein's theory of general relativity, time as we know it cannot be extended beyond that point. It doesn't just get fuzzy or distorted, it disappears. And so we arrive at the idea of a true edge, a moment beyond which there is no earlier, not because we haven't looked hard enough, but because there is no earlier to find. Time, by this account, is not infinite in the past. It has a starting point, a boundary, but that boundary doesn't look like a wall. It's not a place you could stand or a moment you could freeze. It's more like the beginning of a coordinate system. Just as the number line starts at 0 and stretches to the right, time might start at the Big Bang and stretch forward. There's no negative time, not in this view. Nothing to the left, just a beginning. That's a difficult idea to accept. We're trained by experience to believe that everything comes from something, that every effect has a cause, every event has a predecessor. But this model says no, not here, not at the edge. Time itself began at that boundary. There was no moment before it, because without time, there are no moments at all. Still, the question keeps coming back. Could there have been something on the other side of that edge? Some kind of structure, even if not a timeline. Something that existed without unfolding? In certain cosmological models, the answer is yes, but carefully. These models suggest that time is a derived property, not an independent thing, but a feature that emerges from deeper rules, from quantum mechanics, from geometry, from relationships between systems. In these views, time isn't a thread stretched through the universe. It's more like a direction that becomes meaningful only when enough structure exists to define it. One way to picture this is to think about heat. Temperature doesn't exist in a single molecule. It only makes sense when there are many molecules interacting. Their collective motion gives rise to what we call temperature. In the same way, time might not exist in isolation. It might only become real when the universe has enough structure to allow it. And before that structure, no direction, no duration, just potential. Still, there are other ways to think about the edge. One idea is that time didn't have a beginning in the usual sense, because the Big Bang wasn't a singularity at all. It was a bounce, a moment when a previous phase of the universe, possibly contracting, reversed into expansion. In that view, time never stopped. It just changed direction. This leads to what's known as cyclic models. In these, the universe has no true beginning or end. Instead, it oscillates, expanding and contracting over and over, with each cycle erasing the traces of the last. If that's true, then the Big Bang is not an origin, but a transition, a pivot point between eras. There's even a version of this idea rooted in string theory. It suggests that our universe is a three-dimensional brane, short for membrane, floating in a higher dimensional space. Occasionally these branes collide. When they do, they trigger something that looks like a Big Bang. Not just one, but many. Each collision starts a new expansion, and in between, a pause, a reset, a stage beyond time as we understand it. In that view, time continues, but not smoothly. It has edges, gaps, moments that begin not because of internal clocks ticking, but because of external events, like branes crashing or dimensions folding. These theories are still speculative. They stretch our tools and our language, but they help us ask better questions. And even if they turn out to be incomplete, they remind us that the edge of time might not be sharp. It might be smooth. A curve, not a cliff. A rounding off of dimensions rather than a rupture. Stephen Hawking once proposed that time might not have an edge at all, that the beginning of the universe in imaginary time is like the South Pole. You can go south, and then you're there, but there's no more south than that. It's not a boundary you hit. It's just where the coordinate system starts. Maybe time is like that too. Maybe it curves into being, quietly, gradually, without ever needing a moment of creation. That's hard to picture, but it might be closer to reality than we think. The edge, in this model, isn't a mark or a line. It's just the limit of what time can describe. And yet, something lies just beyond that edge, not in distance, but in concept. A place where ideas still make sense, but not yet as moments. Some physicists believe that whatever preceded time must have left an imprint, a memory in the structure of space, a pattern in the background radiation, a signal buried in the statistics of the cosmos. These clues are faint, but we're learning how to look. New instruments are being built to search for gravitational waves from the earliest phases of the universe, to detect the fingerprints of inflation, to listen for echoes from a time before time, and maybe, just maybe, one day we'll find them. For now, we know this much. Time is not absolute. It bends. It slows near massive objects. It stretches with the expansion of space, and it may have had a beginning, not with a flash, but with a change, a shift from stillness into flow. You exist within that flow now. Every heartbeat, every blink, every breath is part of time moving forward. But at the edge, that quiet, unreachable edge, time itself began to breathe. As soon as the word singularity appears in a conversation about the universe, the mood shifts. It's a term that carries weight, partly because it's rooted in advanced physics, and partly because it sounds like the kind of thing stories are built around. It suggests a turning point, a mystery, a place where the rules stop working and something different begins. In technical terms, a singularity is simply a point, or a region, where certain values become infinite, where our equations break down. In the context of the Big Bang, it refers to a moment when density, temperature, and space-time curvature all shoot up to values we can't meaningfully calculate. Not because we haven't tried, but because our best tools, general relativity and quantum mechanics, stop speaking the same language when pushed that far. We know singularities from black holes too. At the centre of every black hole, current theory predicts a singularity, an infinitesimally small point where matter is compressed to infinite density. But again, that's not necessarily a description of reality. It's a flag, a place where the math signals, we don't know what happens here, and that flag appears again when we look back toward the beginning of the universe. If we run the clock in reverse, watching galaxies get closer, temperatures rise, wavelengths shrink, we eventually reach that same wall, a point where general relativity gives up. That's what we call the Big Bang singularity. But calling it a singularity doesn't mean we understand what it was. It means we've reached the limits of the map. And that's where storytelling begins. Because when the math ends, imagination steps in. Carefully, ideally. Grounded in theory, built on models, but still imagination. Different scientific models try to fill in what might lie beyond the singularity. Loop quantum cosmology, for example, replaces the Big Bang singularity with a bounce. In that framework, quantum properties of space-time prevent infinite compression. The universe shrinks, but only to a minimum size, a kind of rebound point, and then begins to expand again. No singularity, just a transition. Other models suggest that the singularity never really existed, that it's an artifact of using classical physics in a realm where quantum rules should dominate. If we had a complete theory of quantum gravity, they argue, the singularity would dissolve, replaced by a finite, understandable state with extreme but manageable conditions. But even these scientific attempts to describe the pre-Big Bang state follow a narrative arc, a before, a turning, an after. That structure, the shape of a story, is hard to escape, because we understand new things by connecting them to what we already know. We reach for metaphors. We use language shaped by plot, tension and release, mystery and revelation, beginning, middle, end. And perhaps that's why the singularity holds such power. It gives us a moment to point to, a once upon a time, even if time didn't exist yet. It offers a way to start the story, but that impulse, to find a beginning, isn't only scientific, it's human. Every culture, across time and distance, has tried to tell stories about where everything came from. Creation myths, origin tales, cosmic genealogies. These aren't science, but they reflect a shared need to put a frame around the unknown, to take the vastness and bring it close enough to touch, even if only in words. The Big Bang has become our modern creation story. It's backed by evidence, by theory, by observation, but it still follows the same shape. Something from nothing. A moment of change, a great unfolding. And within that shape we try to place ourselves. But if the singularity is a placeholder, if it marks the point where the story becomes silent, then we're left with two possibilities. One, it hides a deeper truth we haven't yet uncovered. Two, it reminds us that some beginnings are not beginnings in the traditional sense. They're thresholds, places where different rules apply. In either case, what lies beyond the singularity, before the expansion outside of time, is still an open question, which means there's room for more than one kind of thinking. Scientific models that test predictions, mathematical frameworks that describe boundaries, and also carefully storytelling, not in the sense of fantasy, but as a way to move through uncertainty, to organise what we don't yet know, because even if time had a start, our curiosity doesn't. It keeps reaching, not just for the next answer, but for the next question. And maybe the singularity is the perfect symbol for that. A place where answers run out, but wondering continues. It doesn't matter whether the singularity was real, or just a failure in the math. It marks something important, a transition we still don't fully understand. And the fact that we can even ask about it, calmly, curiously, without rushing, is part of what makes the search worthwhile. We may not be able to peer past it, but we can circle it, describe its shape, try out different stories, informed by physics, rooted in data, but always aware that behind every theory there's a kind of humility, a willingness to admit we don't know yet. When you hear the word bounce, you probably think of something light, a ball hitting the floor and leaping back up, something simple, predictable. But when cosmologists use the word, they mean something far more profound. They're talking about the possible history of everything, not as a one-time event, but as part of a repeating rhythm, a cycle of collapse and expansion, a universe that didn't begin with a bang, but with a rebound. The idea is simple at first glance. What if the Big Bang wasn't a beginning, but a transition? What if, before the universe expanded outward, it was shrinking inward? A previous cosmos, contracting under its own gravity until it reached some limit, and then reversed. This is the heart of the bounce hypothesis, that the universe didn't emerge from a singularity but from a prior state, one where it was already filled with matter, energy, space, and even time. That earlier universe collapsed, compressed, and then something happened to turn that collapse into expansion. It's a tempting idea. It avoids the need for a hard beginning. It makes the universe feel less like a one-off event and more like a system with memory. Cycles instead of origins, loops instead of lines. But it also raises new questions, because a bounce isn't simple. You can't just run time backward and expect everything to work the same in reverse. Entropy, for one thing, doesn't like to decrease. It's a fundamental principle. In a closed system, disorder tends to grow. If a universe collapsed from the one we know now, full of stars and galaxies and black holes, the bounce would have to reverse an enormous amount of entropy, or else carry that disorder forward into the next cycle. And then there's the issue of scale. As a universe collapses, it gets hotter, denser. The curvature of space becomes extreme. Would it really be possible for that state to pass smoothly through the bounce without tearing itself apart? Would space-time survive intact? Some theories say no, but others, especially those exploring quantum gravity, say maybe. In particular, loop quantum cosmology, which applies the principles of loop quantum gravity to the early universe, offers one possible path. In this model, space itself has a kind of granular structure. It's not continuous like a sheet of paper, but made of tiny, indivisible units. When a collapsing universe reaches an extremely small size, quantum effects create a kind of repulsion, not from particles pushing, but from space resisting further compression. This quantum repulsion doesn't destroy the universe. It turns it around. It causes a bounce. In that model, there is no singularity, no infinite density, just a minimum size, the Planck scale, where the fabric of space pushes back. The universe contracts until it hits this threshold, and then begins to expand again. Slowly at first, then faster, eventually becoming the vast cosmos we now observe. And if that's true, then we are living in the aftershock of a previous universe. Not a continuation exactly, but a consequence. A universe born not from nothing, but from the death of another. Other bounce theories come from string theory, where the idea of extra dimensions allows for new kinds of interactions. In one version, our universe is a three-dimensional brain, a membrane, floating in a higher dimensional space. Occasionally this brain collides with another. That collision releases energy, sparks expansion, and what we see as the Big Bang is just the latest of many such events. In that view, the universe doesn't collapse into itself. It crashes into something else. A cyclical process, driven not by gravity, but by the geometry of extra dimensions. Whichever version you explore, the central idea is the same, that the universe didn't begin with a singular point, that it didn't require a moment of absolute creation. Instead, it underwent a transition from one phase to another, a compression followed by expansion, a bounce. This reframes the whole story, because if the universe has bounced before, it might bounce again. Expansion might slow, stop, reverse. The cosmos could begin collapsing, galaxies falling inward, stars drifting together, space itself shrinking, until, once again, it reaches the edge, the threshold, and bounces back. That kind of cycle could repeat endlessly. A universe without a beginning or an end, just phases, epochs, rhythms too vast for anyone life to perceive. Of course, none of this is proven. The evidence for a bounce is indirect and hard to separate from other models. Cosmic microwave background data, the leftover light from the early universe, can sometimes support inflation or bouncing or other structures, depending on how it's interpreted. And that's part of the challenge. We're looking for signs of what happened not just billions of years ago, but in a time before time, or at least before time as we know it. The signals are faint, the clues are buried in noise, but they're not unreachable. If bounce cosmology is correct, it may leave subtle traces, patterns in the distribution of galaxies, signatures in gravitational waves, deviations in background radiation. Scientists are working to find them. Until then, the bounce remains a possibility. A story the universe might be telling, if we know how to listen. And even if it turns out to be wrong, it still offers a powerful way to think. Because it reminds us that beginnings might not be absolute. That what looks like the start could be a continuation. That the universe might carry the memory of something older, something quieter, something collapsing into a form we now inhabit. We don't need to decide today whether the bounce happened. We can just hold the idea, let it settle, let it sit alongside the others, inflation, singularity, quantum birth, each offering a different angle on the same question. Where did this all come from? And is it part of something bigger, a rhythm, a pulse, a deeper flow that stretches far beyond what we can see? Once you've entertained the idea of a bounce, a universe that contracts and then expands, it's not a far leap to imagine that it doesn't just happen once, that the process itself might repeat, not as an accident, not as a rare event, but as a built-in rhythm, a cycle. One universe giving way to another, again and again without end. This is the idea behind cyclic cosmology, that the universe isn't a single event, but a repeating pattern, a system that grows, fades, resets, and begins again. It's not a new thought. Versions of it go back thousands of years. In some ancient philosophies, time itself was seen as circular, not linear. The cosmos wasn't moving toward a final moment, but returning to something it had already known. Hinduism, Buddhism, and certain strands of Greek philosophy all contain echoes of this idea. The world is born, it lives, it dies, and then it comes back. Not just metaphorically, but cosmically. In modern physics, these echoes have found new form, not through myth, but through mathematics. Theories that explore whether our universe could be part of a chain, one cycle nested inside another. There are different versions of how it might work. In one, the universe expands for a long time, then slows down, reverses and collapses, only to bounce and begin again. In another, the universe doesn't collapse, but stretches so far that it dilutes itself into silence. Then, through some subtle transition, it resets, with the expansion starting over from a tiny high-energy state. One of the more developed models is called the ekpyrotic universe, from a Greek word meaning conflagration or cosmic fire. In this theory, our universe is a brain, a three-dimensional surface, floating in a higher dimensional space. There is another brain parallel to ours. The two attract each other slowly, over vast spans of time. Eventually they collide. That collision releases energy, creating the conditions for a new universe. Expansion begins, galaxies form, life emerges, and then, far in the future, the brains begin drifting apart again. Space cools, structures fade, but the attraction remains. The cycle continues. A new collision, a new burst, a new universe. What's compelling about these models is that they allow for an infinite series of cycles, each one giving rise to the next without needing a hard beginning. Time in this picture stretches endlessly backward and forward. There's always a before, always a next, but the challenge lies in memory. If universes are born and reborn, do they remember each other? Does anything carry over? Do patterns repeat? Some cyclic models suggest that each new universe is truly fresh, a clean slate. The entropy resets, the structures vanish. No trace remains of what came before. Others propose that small imprints might linger, tiny asymmetries, fluctuations in the cosmic background, something faint but detectable. And then there's the philosophical question, the one that arises naturally when you imagine infinite cycles. If everything happens over and over, does that mean we've lived this life before? Does the same configuration of atoms, of thoughts, of choices, reassemble somewhere, sometime, in another cycle? This idea is sometimes called the eternal return. It's not a scientific theory in itself, more a philosophical consequence of a cyclic universe with limited configurations. If space and time are infinite and matter is arranged randomly, then sooner or later the same arrangement might appear again. Not just similar, but identical. You, sitting where you are, thinking what you're thinking, might be a recurring note in an infinite melody. Of course, this depends on how time and probability actually behave at cosmic scales. In most scientific models, the number of possible configurations is staggeringly large. So large that exact repetition is almost meaningless to consider. But the idea still lingers, not as a prediction, but as a thought. A reminder that in a universe without finality, nothing is ever entirely new, or entirely lost. From a scientific standpoint, cyclic models offer one appealing feature. They avoid the need for fine-tuned beginnings. They don't require a special starting condition or a perfectly balanced inflationary phase. They let the universe evolve gradually, cycle after cycle, ironing out irregularities with each pass. But they're not without their complications. For one, there's the issue of entropy. In classical thermodynamics, each cycle would accumulate more disorder. If that trend continues forever, then each new universe should be messier, more diluted, less structured than the last. Eventually, the cycles would decay. To solve this, some theories propose mechanisms for entropy to be removed or rebalanced during the transitions. Others suggest that our understanding of entropy might change at extremely high energies, or that quantum gravity could rewrite the rules near the bounce. These are open questions. The math is complex, the observations are limited, but the concept remains alive because it offers something unique. A view of the universe that doesn't need a beginning, doesn't need an end, and doesn't need to explain everything with a single spark. Instead, it offers repetition, motion, rhythm, a universe that breathes in and out over and over across scales of time too large to name. That's not an answer to every question, but it changes how you ask them. Instead of wondering what came first, you begin to wonder how long this has been going on. Instead of asking what started it all, you ask what keeps it in motion. What holds the cycle together? What patterns repeat? And maybe more importantly, what changes? Because even in a repeating universe, not every cycle is the same. The details shift. The outcomes vary. New galaxies form. Different lives unfold. It's not just a copy and paste. It's variation within structure. A familiar shape, filled with new content every time. You may never see the whole pattern. No one life is long enough. No single perspective can stretch that far. But you can imagine it. You can hold the idea. That what you see now, stars, planets, breath, thought, is part of a rhythm far older than anything we've recorded, a cycle still turning. Up to now, we've been speaking mostly in terms of what we can see. Space expanding, time unfolding, universes cycling. But some theories go deeper, asking if what we call space and time are just part of something larger. Not just larger in size, but in kind. Something with more dimensions than we experience, more structure than we've yet mapped. And in that larger framework, there's an idea that stretches the imagination again. That our entire universe might be a kind of surface. A three-dimensional shape embedded in a higher dimensional space. This is where brains come in. Short for membranes, brains are fundamental objects in string theory. A framework that tries to unite quantum mechanics and gravity into a single coherent picture. In string theory, particles are not point-like, but tiny vibrating strings. Their vibration patterns give rise to mass, charge, spin. But those strings don't exist in just 3 dimensions of space. For the math to work, they need more, usually 9 or 10 spatial dimensions, plus 1 for time. Most of those dimensions, according to the theory, are tightly curled up, compactified into tiny loops too small to detect. But some may be larger, even infinite. And it's in those larger dimensions that brains begin to play a role. Imagine for a moment a sheet of paper floating in a room. The paper is 2-dimensional, length and width, but the room is 3-dimensional. You could live your whole life as a tiny creature on that sheet, moving left and right, forward and back, never realizing there's a 3rd dimension above and below. You'd think your universe was all there is. You wouldn't know it was sitting in a bigger space. Now imagine our universe is like that sheet. A 3-dimensional brain floating in a higher dimensional space. Everything we know, every particle, every star, every field, exists on that brain. Light, gravity, chemistry, biology. All of it confined to the surface. We live entirely within it. But the space it floats in, or called the bulk, could contain more. Other brains, other universes, other physics. In some models, gravity is the only force that can leak into the bulk. That might explain why gravity is so much weaker than the other forces. It spreads out. It's diluted. While electromagnetism, the strong force, the weak force, they all stay trapped on the brain. This idea opens the door to something dramatic. That the Big Bang, the origin of our universe, might have been caused by a collision between brains. In particular, one version of this idea comes from what's called M-theory, an extension of string theory that incorporates 11 dimensions. In this view, our universe is one of 2 parallel brains, slowly moving toward each other in the bulk. Over immense stretches of time, their motion brings them close, and when they collide, the energy released creates the hot, dense conditions of a new universe. Not a universe out of nothing, but a universe from interaction. The matter, radiation and structure we now observe could be the result of that collision. A brain crashing into another, triggering expansion, heating space, creating particles. Then, as the brains move apart again, the universe cools, structures form, and time as we know it continues. This framework offers a version of cyclic cosmology too. In some models, the brains move in a repeating path. They approach, collide, expand, move apart, and then gravity pulls them back again. Each collision is a new beginning, a new big bang, a new cycle. It's a different way of thinking about origins. Not a single point exploding outward, but a dance in higher dimensions. Not a sudden birth, but a repeated event. Regular, if slow. The idea of brains also helps address some problems in early universe cosmology, like the fine-tuning needed for inflation, or the question of why the universe is so smooth on large scales. Colliding brains could provide a natural mechanism for these features, smoothing out irregularities before each new cycle begins. But just like other models we've talked about, this one is still speculative. The mathematics is consistent, but the evidence is hard to collect. We don't have instruments yet that can detect higher dimensions directly. We don't know if the bulk exists. We don't know what brains would be made of, or how to test their motion. Still, the theory offers predictions, certain patterns in the cosmic microwave background, signatures in primordial gravitational waves, deviations from expected inflationary results. Scientists are looking for those hints, because if they appear, they could point toward a universe embedded in something even larger. And if that's true, then everything we experience, space, time, energy, is only part of the picture. A surface, a layer, a ripple in a larger sea. That doesn't make what we see less real. It just places it in context, like realizing that your city is one part of a continent, or your planet one part of a solar system. Scale doesn't change truth, it just gives it depth, and it gives us more to explore, not just physically, but conceptually. Because higher dimensions aren't just coordinates on a map. They represent ways the universe might be structured beyond our direct perception. They hint at the possibility that the story we tell, of beginnings, of expansion, of space and time, is part of a wider narrative. A brain might not sound poetic, but it represents something poetic in its implications. That our universe is not alone, that there could be others, close and yet unreachable, brushing against ours, shaping its history. Maybe every so often two brains meet, not by accident, but by the rules of motion in a deeper geometry. And when they do, a new universe sparks, not because of a creator, or a moment of pure chance, but because of physics, carried out in a space we can't yet see. If that's true, then our universe carries the memory of that meeting, in its expansion, in its structure, in the quiet glow of its background radiation, a leftover light from a moment of contact. You're part of that story now, living on a surface, moving through space, experiencing time, but shaped by something bigger, folded just beyond perception. By now, the idea that our universe might not be the only one is no longer just a whisper on the edge of science fiction. It's something being taken seriously by physicists, not because it's comforting or imaginative, but because it naturally arises from certain theories. You begin by asking about the origins of this universe, its shape, its structure, its rules, and you end up in a place where it becomes difficult not to imagine others, different, parallel, separate, or connected in strange, invisible ways. The word multiverse carries weight. It sounds almost too big to hold. But at its core, it's a simple idea that our universe, everything we can see and measure and understand, might be just one pocket in a much larger reality. Not the whole, but a part. Not unique, but one variation. This doesn't mean science is abandoning the idea of a singular cosmos. It means some of our best models, the ones that fit the data, point toward a reality that includes more than we can directly observe. One path to the multiverse begins with inflation, the rapid expansion that's thought to have occurred just after the Big Bang. In some versions of inflation theory, space doesn't stop inflating everywhere at once. Instead, some regions stop expanding and settle into normal space, like our universe did, while other regions keep going. Those keep stretching, and within them, new pockets stop inflating too. Each pocket becomes its own universe, with its own laws, constants, and structures. This is called eternal inflation. It's a universe that keeps generating new universes, not by design, but as a consequence of the physics involved. The process never stops. It creates an endless tree of branching realities. Some might look like ours, others might be wildly different. In one pocket, gravity might be stronger. In another, atoms might not form. In another still, stars might never ignite. The rules vary because the conditions that settle out after inflation can shift from one bubble to the next. Each one is a separate cosmos, with its own space and time, its own version of physics, and no clear way to reach or communicate with the others. That kind of multiverse is known as the cosmic multiverse, born from inflationary theory. But there are other kinds too. Quantum mechanics, for instance, leads to another version. According to the many worlds interpretation, every quantum event, every time a particle could take more than one path, actually branches. Not metaphorically, literally, the universe splits. In one version, the particle goes left. In another, it goes right. Each possibility plays out, and the result is an ever-dividing tree of outcomes. Every choice, every randomness, spawning new branches. From your point of view, it feels like one thing happened, one timeline. But from the perspective of the full quantum state, everything that could happen does happen, just not all in the same version of reality. That idea leads to a multiverse of histories, not bubbles floating in space, but timelines branching in possibility. A structure so large and subtle that most of it will forever be inaccessible to you, not because it's far away, but because it runs parallel to your own path. Then there's the landscape of string theory. If that theory is correct, and the universe has extra dimensions shaped in specific ways, then there are vast numbers of possible ways those dimensions can fold. Each configuration leads to a different version of physics, different particles, different interactions, different universes. The number of possible configurations is immense, sometimes estimated as 500 or more. That's not a poetic exaggeration, it's what the math allows. Each configuration describes a different kind of universe, and there's no rule, in the theory, that says only one is allowed, which leads to the possibility that all of them exist, not in the same space, not on a map you could draw, but in the broader reality that string theory describes. So you end up with a multiverse from inflation, a multiverse from quantum mechanics, a multiverse from string theory. Some scientists are cautious about all this. The multiverse is hard to test, hard to falsify. We can't reach these other universes. We can't run experiments on them. But others argue that we don't need to. If a theory predicts a multiverse, and that theory explains everything we can see better than anything else, then we're still learning something real, and there may be ways, someday, to test the edges. Some models predict that universes can collide. If that happened, there might be a subtle imprint in our cosmic microwave background, a circular pattern, a symmetry that shouldn't be there otherwise. We haven't found anything conclusive yet, but we're looking, because the multiverse, if it exists, changes the context of everything. It means our universe's properties, the fine-tuning of physical constants, the balance that allows atoms and stars and chemistry to exist, might not need a deeper reason. They could just be one draw from a much larger deck, and we're here to observe them because we live in one of the rare places where observers can exist. That's not giving up on explanation. It's a shift in how we frame it. We stop asking, why is the universe this way? And start asking, why is this the version we observe among all the possible ones? The multiverse doesn't make your universe smaller. It makes it part of something larger, a background of infinite variation against which our own branch, or bubble, or brain becomes visible, specific, real. Not because it's the only one, but because it's the one you're in. And when you think about it from this perspective, from the idea that the laws of physics themselves might be local rather than universal, you begin to see how the search for origin becomes even more intricate. What we call the beginning might not be the beginning of all things, just the start of this local patch, this timeline, this unfolding. The murmurs of a wider multiverse continue just out of reach. But sometimes, even if we can't hear them clearly, we can sense their presence in the questions that remain, in the symmetry that seems too elegant to be chance, in the constants that sit just right for life to emerge. Maybe the multiverse is real, maybe it isn't. But the idea, grounded in theory, shaped by observation, alive in the mathematics, continues to echo. It's a question that never quite goes away. No matter how far back we trace the physics, no matter how many theories fill in the blanks, at some point someone asks it directly, could the universe have come from nothing? Not from another universe, not from a bounce, not from a higher dimensional collision or a quantum fluctuation inside a vacuum, but from genuine, total, absolute nothingness, and not the kind of nothing we sometimes mean in everyday conversation. An empty room, a blank page, a place without objects. Those are still things, still structured, still resting inside space and time. The kind of nothing we're talking about here is more radical. No space, no time, no particles, no fields, no rules, just absence. The absence of everything. Not even a framework to place absence inside. It's hard to picture, and maybe that's the point. Because human minds are built to work with something, even if that something is minimal. We need context. We need contrast. A true nothing strips all of that away. It leaves no place to stand, no coordinates to think with, no past or future to stretch toward. And yet, some physicists have tried to describe how a universe might emerge from that. Not metaphorically, not philosophically, but mathematically. One approach comes from quantum cosmology, a field that applies the principles of quantum mechanics to the entire universe. In this framework, the universe doesn't need a cause in the traditional sense. It can appear spontaneously due to the laws of quantum physics. The idea is that the vacuum, even a true perfect vacuum, is not completely stable. Quantum fluctuations can cause configurations to appear temporarily, with tiny unpredictable properties, and under certain conditions one of those fluctuations might not disappear. It might grow, it might evolve, it might become a universe. This is sometimes described as a quantum tunneling event, where the universe tunnels from nothing into existence. The transition isn't through space or time, because space and time don't exist yet. It's a mathematical possibility, a change in boundary conditions. Stephen Hawking and James Hartle developed a model along these lines. In it, the universe doesn't begin with a singularity, but with a smooth curved geometry that transitions from a timeless, spaceless quantum state into the classical universe we now observe. This is called the no-boundary proposal. It doesn't require an edge. It doesn't require time before time. The universe simply is and then begins to evolve. That raises the question, what allows this kind of transition? What causes the universe to appear? And here the word cause might be misleading. Because in quantum mechanics, events don't always require causes in the way we're used to. A particle can appear, uncaused, from a vacuum. It's not magic, it's not arbitrary. It's a result of probability fields and uncertainty. In this sense, the universe could be the ultimate quantum event, the largest scale fluctuation possible. Once it begins to expand, it brings its own time and space with it. It creates the stage on which its history will play out. The energy that drives its expansion, often modelled as vacuum energy or a false vacuum state, doesn't come from somewhere. It doesn't need a source. In these models, the total energy of the universe can be exactly zero. Positive energy from matter and radiation is balanced by negative energy from gravity. That balance allows the whole structure to exist without violating conservation laws. If the total energy is zero, then in a way, the universe costs nothing to make. That phrase, the universe from nothing, can be misleading if taken too literally. It doesn't mean there was a factory of nothingness where universes are manufactured. It means that within the mathematical frameworks we use, a universe like ours can arise spontaneously, without violating physical principles, without requiring anything external. It's not a complete explanation. There are still assumptions built in. You still need laws. You still need quantum mechanics. You still need the mathematical fabric that defines possibility. And then people ask, rightly, where those come from. Because even a universe from nothing is still shaped by something. Not something in space. Not something made of matter. But something abstract. A system of logic, structure, rules. Are those rules eternal? Did they always exist? Is there such a thing as always, outside of time? At this point, physics begins to blur into philosophy, into metaphysics. Some argue that the laws of nature are necessary truths, that they don't come from anything because they couldn't be otherwise. Others suggest that even the laws might be emergent, that they too evolved or were selected for in some broader framework we don't yet understand. But the fact remains. Our universe behaves as though it could have emerged from an extremely simple initial state, or even from the absence of a state, through mechanisms allowed by quantum theory. That's a remarkable idea. It doesn't close the book, it opens it. It invites deeper questions. If this is one way for a universe to begin, are there others? Are universes common given the right abstract conditions? Or is this one rare, even among the uncaused? And most personally, what does it mean that everything around you, space, time, stars, thoughts, might rest on something as intangible as a fluctuation? Not random, but not commanded either. Just allowed. You're here now, living in that permission. In a space where particles coalesced, forces shaped complexity, and atoms arranged themselves into brains that could wonder where they came from. Maybe we don't need to imagine a spark, a builder, a moment of creation in the traditional sense. Maybe the universe doesn't come from something. Maybe it is what happens when nothing is unstable, when the absence of structure doesn't last. And what follows isn't disorder, it's the most intricate order imaginable. Galaxies, gravity, sunlight, breath. None of that answers every question. But it reshapes what the questions are. Not just what caused this, but what kind of reality allows it to happen at all. And if the answer is one where something can arise from nothing, then perhaps this universe is not impossible, not improbable, just one of many things that can happen when the rules, whatever they are just right. When we talk about the beginning of the universe, most models describe a starting point, a moment where time equals zero, space is incredibly dense, and everything we know begins to evolve. But even that description assumes time itself exists at the beginning, that there is a before and an after, that there's a direction, a flow. Stephen Hawking once suggested a different approach, not just a different story, but a different kind of time. He called it imaginary time, and despite the name, it's not fiction. It's a mathematical tool, drawn from complex numbers, used to describe what happens when our usual understanding of time breaks down. In imaginary time, the timeline isn't a straight line with a clear beginning and end. It becomes something else entirely. To understand what Hawking was proposing, you first need to step back from how we usually think about time. In everyday life, time is one-dimensional. It moves forward. It has a past, a present, a future. It flows. But mathematically, time can be treated as a coordinate, just like the three dimensions of space. And in quantum mechanics and general relativity, we often manipulate that coordinate by substituting real time with imaginary numbers. Numbers that include the square root of -1. It sounds abstract. It is. But this substitution transforms the equations in a way that makes certain problems more manageable, especially in quantum cosmology, where we're trying to model the early universe, before it had a classical structure. Hawking, along with physicist James Hartle, proposed that near the beginning of the universe, time behaves more like space. That instead of being a timeline with a sharp origin, the early universe is shaped more like a sphere, smooth, finite, with no boundary. Think of the surface of the Earth. It has no edge, no starting point. You can walk around it forever. But there's no place where the surface begins. If you stand at the South Pole, you've reached the bottom. But there's no edge there, just a smooth rounding, no cliff, no break. Hawking imagined time in a similar way. In his model, time near the origin of the universe curves smoothly into space. No singularity, no infinite density, just a rounded-off geometry, described using imaginary time. From that curved, timeless state, the universe transitions into real time, the kind we experience now, as it expands and cools. This proposal is known as the no-boundary condition. It suggests that the universe is self-contained. It has no edge in space and no beginning in time. At least not in the usual sense. Time, according to this model, doesn't start with a bang. It emerges gradually, out of a state where distinctions between time and space don't yet exist. That might sound like a way of dodging the question of beginnings, but it's not. It's a direct attempt to replace the singularity, the point where the math breaks down, with a well-defined finite geometry, one that doesn't require something before, one that doesn't rely on anything outside the system. The use of imaginary time isn't unique to cosmology. It appears in quantum field theory, in statistical mechanics, in path integrals used to calculate probabilities. But in the context of the universe as a whole, it becomes something more than a tool. It becomes a way to describe the early structure of space-time itself. Of course, imaginary time isn't something you can experience. You don't feel it. You can't observe it directly. But the idea allows physicists to describe a universe without the sharp edge of a beginning, without a boundary that demands explanation. In Hawking's view, this helps resolve the puzzle of what came before, because if time didn't exist in the earlier state of the universe, if it curved into being from a more fundamental timeless structure, then the question of before loses its meaning. It's not that something prevented a before, it's that the concept never applied. This is a subtle shift, but a powerful one. It means the universe might not require an external cause. It might not need to be created from outside. It might not need a triggering event. It simply is. Complete, finite, curved in imaginary time, and then unfolding into the reality we observe. Does that mean the universe is eternal? Not necessarily. Just self-contained. The no-boundary proposal doesn't make claims about infinite duration. It describes a beginning that isn't a break, a geometry that includes its own origin as part of its structure. Like any theory, this model is still subject to debate. Some physicists question whether imaginary time corresponds to anything real. Others argue that while the math is consistent, it might not reflect how the universe actually began. But what Hawking offered wasn't just a clever workaround. It was a serious attempt to describe a beginning that didn't require special pleading, that didn't need to insert a moment of creation by hand, and in doing so he reframed the question. From what caused the universe, to how does the geometry of space-time naturally include its own origin? It's not an answer to every problem, but it's a shift in perspective, a different shape to the map. one that replaces a point with a curve, an edge with continuity. And if it's right, or even close, then the earliest moments of the universe weren't a flash or a rupture. They were a rounding, a smooth emergence from something that didn't yet carry the weight of time. We still live in the wake of that curve, moving forward in the version of time that settled in after the transition. But underneath it all might still be the echo of that imaginary state. Not imaginary in the sense of fantasy, but in the mathematical sense. Real in its own way, just hidden behind the way the universe now works. Long before physics tried to describe the beginning of the universe in terms of imaginary time, singularities, or quantum fluctuations, people were already asking where everything came from. They didn't have telescopes or equations, but they had stories, and in those stories a different kind of structure emerged, not mathematical, but symbolic, a way to hold the vast unknown in something small enough to grasp. Among the oldest and most widespread of these stories is the idea of the cosmic egg, a closed, self-contained origin from which the universe hatches or unfolds. You can find versions of this motif in cultures across continents, separated by geography and time. In ancient Hindu cosmology, the universe begins from the Brahmanda, the cosmic egg, which floats in a vast primordial sea. It holds all potential within it, dormant and complete. Then it breaks, or blooms, and the world begins. Not through a spark or a voice, but a gentle unfolding. In Chinese mythology, there's a similar image. The universe begins as a formless chaos, enclosed in an egg. Inside it, the figure Pangu sleeps. When he wakes, he cracks the shell. The lighter parts rise to become the heavens, the heavier ones fall to form the earth. Pangu grows as the cosmos separates, holding the sky and ground apart. Eventually he becomes the mountains, rivers and winds. The Greek philosopher Orphics told a version too. The first being, Fons, is born from a cosmic egg created by night. He emerges with golden wings, bringing light and order to the universe. The egg is not explained. It simply exists. A shape before time. There are dozens of other versions, in Polynesian myths, in Finnish folklore, in African cosmologies. The details change, the meanings shift, but the image of a world born from a closed, smooth, self-contained form repeats. It's not hard to see why. The egg is simple, it's complete. It contains life in potential. You don't see what's happening inside, but you trust that something is. There's a quietness to it, a sense that things are preparing, not yet revealed, and that resonates with how many modern cosmological theories describe the early universe. Not in symbolism, but in structure. Inflationary models often describe the universe as beginning from a tiny uniform state, one that expands exponentially, then cools and gives rise to the complexity we now observe. That initial state is dense, symmetric, featureless. In some ways it functions like an egg, closed, self-contained, holding structure that has not yet unfolded. Other models, like the no-boundary proposal, describe the universe as smooth and curved, without edge or singularity, a shape that could be mapped onto a higher dimensional version of a sphere. Again, no sharp boundary, no external shell, just a complete form. Even quantum cosmology sometimes uses language that sounds familiar, describing the universe as emerging from a timeless state, from a bounded configuration in a probability space, with all possible outcomes folded inside. No defined origin, but a place where structure incubates before it becomes observable. It's not that modern physics borrows from these ancient myths. The math and mechanisms are different. The language is precise. The claims are testable. But it's striking how often the ideas align in shape, if not in purpose. Because whether it's an egg in a creation myth or a closed geometry in quantum gravity, both are attempts to describe the same thing. How something that looks empty can hold everything. How what seems smooth can contain seeds of complexity. How the visible might emerge from the hidden. The myths gave form to wonder. The equations give form to prediction, but the impulse is the same, to hold the universe in a single concept, a place where it all begins, not as an explosion, not as a command, but as a quiet, enclosed potential. Of course, science and myth aim at different kinds of truth. One is provisional, revised by evidence. The other is interpretive, passed through generations. But both, in their own way, try to answer what happens when we ask what came before. And sometimes the stories echo each other. Not because one is copying the other, but because the structure of beginnings, the need to find containment before expansion, leads naturally to similar shapes, a universe born from a shell, a space that expands only after something internal has matured, an unfolding that happens not from outside force, but from internal readiness. In the myths, the egg breaks. In the models, the symmetry breaks. In both, the break is not destruction, it's transition. A move from stillness to motion, from hidden to visible. None of this proves anything. But it offers a reminder that our need to explain beginnings is older than physics, and that some of the shapes we now describe with geometry and fields have been felt before, in different languages, with different tools. Maybe that's not a coincidence. Maybe the human mind, in its search for origins, naturally finds certain forms comforting. A circle, a shell, a closed, waiting space. And maybe it's no surprise that when we look at the early universe, when we try to model its geometry, its behaviour, its potential, we often find that the cleanest solutions, the most consistent results, come from structures that feel like those ancient symbols. Rounded, smooth, self-contained. Not because myth was right, not because science is retelling the same story, but because some ideas, when shaped by deep questions, come back again, not as answers, but as forms. And the form of the cosmic egg, simple, quiet, enclosing everything, is one that still works, even now. The deeper we go into the question of origins, the more precise the models become. Quantum fields, inflation, brains, probabilities. But also, the more apparent it is that some questions remain just out of reach. Not because they're unimportant, not because no one's looking, but because right now there are things science simply doesn't yet have the tools to explain. This isn't a weakness. It's part of how the process works. Science doesn't rush to fill in every gap. It holds space for what hasn't been tested, for what hasn't been measured. The unknown isn't a flaw in the system. It's a sign that the system is still working, still asking, still adjusting. And so, when we ask questions like, what came before time? Or, why does the universe exist at all? We often find ourselves standing at the edge of what current theory can offer. Not because no one has tried, but because the structure of the question itself doesn't yet align with the structure of what can be tested. For instance, we don't know exactly how to combine general relativity, which describes gravity and the structure of space-time, with quantum mechanics, which governs the smallest particles and forces. Both frameworks work incredibly well in their domains, but when applied to the same object, like the universe at its earliest moment, they clash. They produce infinities, contradictions, gaps. A full theory of quantum gravity would help. It would unify the smooth geometry of relativity with the probabilistic nature of quantum theory. It would tell us what happens when matter is dense enough to warp space-time at quantum scales, black holes, singularities. The first moments after the Big Bang, or before it, if such a thing can even be defined. But that theory doesn't exist yet. Not fully. Candidates like string theory and loop quantum gravity offer promising directions. They give partial answers. They build frameworks. But so far none of them have been confirmed experimentally. And without experimental confirmation, there's a limit to what science can claim. We also don't know where the laws of physics themselves come from. We can describe them. We can measure how they operate. But why they are the way they are, why the speed of light has the value it does, why gravity is weaker than the other forces, why particles have the masses they do, remains uncertain. Some explanations suggest these values arise from symmetry breaking. Others propose selection through the multiverse, where different patches of reality settle into different sets of rules. But we don't yet know whether these patterns are necessary or just convenient, whether they're unique to this universe, or if they emerge naturally from a deeper system we haven't discovered. And there's the question of time itself, not how it passes, or how it can be measured. We understand that well enough. But what it is, why it flows in one direction, why we remember the past but not the future, why entropy increases, these are still open questions. Science can describe time's behaviour, but its deeper nature remains unclear. Then there's the matter of boundaries. Can we ever observe or interact with other universes if they exist? Could a signal from before the Big Bang reach us in any form? Could time have extended into the past through some alternate dimension, or was it really the beginning of all structure? Right now, we don't have access to the data we'd need to answer those questions definitively. Cosmic background radiation, gravitational waves, particle behaviour, these offer clues, but they don't reach far enough back to resolve every theory. The earliest moments are veiled, not because they're hidden by design, but because light and matter hadn't yet separated in a way that left observable marks. This means we're always working with partial information. Every model is tested against what we can see, not what we wish we could see, and for now, that means accepting limits, but limits aren't the same as endings. Science doesn't need to claim certainty to make progress. In fact, some of its most valuable insights come from knowing what can't be said yet, from being honest about the unknown. What we can say is that the universe behaves in consistent, measurable ways, that its large-scale structure matches predictions from models like inflation, that particles interact with astonishing reliability, that gravity, electromagnetism, and the nuclear forces follow rules that hold across space and time. What we can't yet say is why all of that exists, or whether it had to, or what preceded it, if anything. And for some, that's uncomfortable. The impulse to find an answer, a final one, a satisfying one, is strong. But for science, satisfaction isn't the goal. Understanding is. And understanding doesn't always come quickly. Sometimes we just have to wait, to refine the models, to improve the instruments, to ask better questions, to let the unknown stay unknown for now. And that's not the same as giving up. It's the opposite. It's trusting that not every question has to be answered today, that there's value in patience, in precision, in clarity about what we do and don't yet know, because what science can't yet say isn't silence, it's preparation. The theories will evolve, the observations will sharpen, and some of the questions we ask now in uncertainty will one day seem straightforward, as clear as orbits, as clean as spectra, as mapped as the sky. Until then, the unknown is a space we live inside, not as something to fear, just something to explore. So much of the conversation about origins leads to questions about time. When did it start? What came before? Could it extend backward without end? Could it loop? Could it stop? And underlying all of those questions is something more personal, more internal. Not just how time works, but how it feels. Time for us is experienced moment by moment. We track it with clocks, calendars, aging. But alongside that measurable version is something else, a sense, a perception, a feeling. And when we start talking about things like infinite time, eternal cycles, or universes without beginnings or ends, it challenges that perception. Because time in the scientific sense can stretch endlessly, but time in the personal sense is immediate, close, framed by memory and expectation. Still, the idea of forever keeps coming back, not as a conclusion, but as something we naturally reach for when thinking about the biggest questions. If the universe had a beginning, what came before? If it didn't, how far back does it go? If there was no time before time, What kind of non-time could exist? These questions don't always lead to specific answers, but they show that when we think about the universe, its scale, its age, its future, we run up against the limits of what our minds are built to hold. Infinity isn't something we see directly. It's a concept, a structure, a tool in mathematics. But it affects how we think. It creates a sense of openness, of never reaching the bottom or the edge. Some cosmological models embrace that. Eternal inflation, for example, suggests that while our observable universe had a beginning, the larger process that gave rise to it may have no beginning at all. Space keeps inflating. New universes keep forming. There's no single moment of creation, just a process that continues without end. Other models describe time as cyclic, with one universe giving way to the next in an endless series. No first, no last, just iteration. And then there's the possibility that time itself is emergent, that it isn't fundamental, but arises from deeper structures. If that's true, then asking how long the universe has existed might be like asking how long a wave has lasted, without first describing the ocean. All of this pushes on our sense of duration. It makes us ask what it really means for something to go on forever. Does it mean infinite moments, stacked one after another, or something outside of moments altogether? From a physics perspective, the answer depends on the model. Different theories define time differently. Some treat it as continuous, others as discrete. Some think it had a beginning, others think it didn't. But from a lived perspective, from the human view, forever is harder to grasp. It's not just long, it's unbounded. It has no reference point. That can be unsettling, but it can also be grounding. Because when you stop looking for the edge, when you accept that time might not end, or might not have started in the way we usually think, the pressure to find a final explanation eases. You don't have to compress everything into a neat origin story. You can just look around where you are and let the openness be part of the picture. It doesn't mean giving up on explanation. It just means recognizing that the feeling of forever isn't always something that needs to be solved. Sometimes it's just a condition we're living in. Science continues to study the structure of time, its arrow, its curvature, its quantum nature. These are real questions with real implications. But there's a difference between time as a variable in an equation and time as it sits in the mind. We experience the present as a thin slice, flanked by memory on one side and possibility on the other. When we stretch that view toward forever, we reach a place where perception and theory begin to diverge. Still, even if we can't experience infinity, we can think about it. And maybe that's enough. Maybe imagining a universe without edges is part of what lets us ask the next question. Maybe the concept of eternity is one of the tools we use, not to answer everything, but to frame the questions clearly. Because forever isn't just a length of time, it's a way of looking at existence without trimming it down, without stopping it at a convenient moment, without needing it to wrap up. That doesn't mean everything lasts. Stars burn out, galaxies fade, particles decay. But the framework that holds all of that, space-time itself, may not have a final clock. It may just stretch on, reshaping, resetting, redistributing energy in different forms. Whether or not time began, or ends, or loops, or emerges from something deeper, the fact that we can even consider those possibilities is significant. It means the scale of our thinking can exceed the scale of our immediate lives, and that matters. Because even in the smallest slice of time, a single thought, a single moment of awareness, there's contact with something bigger, something that doesn't need to be fully known to be real. We live in one particular configuration of the universe, one version of space, one form of time, but the structures that allow this version may extend far beyond what we can observe, not just in space, but in duration. You won't reach the end of it, not in one life, not in 1,000. But the feeling of forever doesn't need to be reached. It's not something you walk toward, it's something you're already in. After all the questions, all the models, all the diagrams and data and careful reasoning, there's still something that doesn't quite go away. Not a missing fact, not a gap in logic, but something quieter. A feeling that even with the best explanations available, there's still a part of the picture that resists being filled in. It's not failure. It's not even doubt. It's just the recognition that some parts of reality don't resolve cleanly into answers, and maybe they're not supposed to. Maybe part of what makes a question meaningful is that it doesn't have a single final response. The origin of the universe is one of those questions. We've explored bounce models, quantum fluctuations, brains, multiverses, time loops, imaginary coordinates. Each theory brings clarity to one part of the picture. Each one makes predictions, solves problems, refines what came before. But none of them erases the basic truth. We are still trying to understand why there is something rather than nothing, and how that something came to be this particular kind of something. And maybe that's okay, because underneath the science, and not in opposition to it, is something just as real: wonder. That slow, steady sense that the world is more than what it explains, that it goes on unfolding even when we don't have the right words for it yet. Holding the mystery gently doesn't mean giving up on clarity. It just means recognizing when clarity hasn't arrived, and not rushing to replace it with certainty that hasn't been earned. In science, this looks like caution, careful conclusions, open questions left open, the acknowledgement that a model might be elegant but still untested, that a theory might solve a problem but still depend on assumptions we can't yet verify. In life, it looks a little different. It might be the feeling of sitting quietly with an idea you can't fully define, or noticing that the more you learn, the less you're bothered by not knowing everything, or realizing that mystery isn't something to escape. It's part of what keeps your attention awake. We live in a universe with structure. That structure is astonishing in its consistency, its depth, its beauty. But we also live in a universe where some things are hidden, or maybe just not yet visible. We study what we can, using the tools we've built: equations, telescopes, accelerators, simulations. We gather light from distant galaxies. We chart the afterglow of the Big Bang. We watch particles collide. We model the birth of time in computer code. And still, there's a quiet place in the middle of it all that stays unresolved. It's not a flaw in the system. It's not a mistake in the math. It's just the shape of where we are. Aware enough to ask big questions, limited enough not to answer all of them. There are ways to respond to that. You can get impatient. You can try to fill the gap with whatever feels comfortable. A story, a symbol, an explanation that settles the mind. Or you can do something else. You can sit with the mystery as it is. Let it remain open. Let it hold its shape, without trying to smooth it over. That's not indecision. That's a kind of attention. A willingness to see clearly, even when what you see isn't finished. Some questions might not resolve in your lifetime, or in any lifetime. The nature of time, the structure of origins, the boundaries of what exists. These are slow questions. They evolve across centuries, across cultures, across disciplines. But they're still worth asking, not because we need quick answers, but because asking them expands the space of what's thinkable. It stretches the boundaries of what we expect, and sometimes it leads to unexpected clarity in places we didn't know were connected. So you hold the mystery, not tightly, not defensively, just enough to stay aware of it. Like a puzzle piece you don't have a place for yet. Not discarded, not forced into the wrong spot, just waiting, present. This isn't about awe for its own sake. It's not about making the unknown seem dramatic. It's about respect. For the questions, for the process, for the reality that's bigger than what we currently understand. When we talk about beginnings, about what came before the Big Bang, or what might lie beyond the observable universe, we're talking about ideas that stretch not just science, but thought itself. We're asking about conditions that may not fit into space and time as we know them, and we're trying to do that with tools built inside the system we're trying to describe. If you keep following the trail backward, past stars and galaxies, past the glow of the cosmic background, past the earliest known particles and the first flickers of structure, you arrive at a space that isn't quite space, a moment that isn't yet a moment, a state of reality before light, before direction, before measurement. This isn't something we observe directly. The universe was opaque before it cooled enough for light to travel freely. But the models let us approximate what came just before that clarity. Dense, hot, uniform, and full of potential. And if you keep following still, even that begins to dissolve. Before expansion, before inflation, before geometry stabilized, we're left with conditions that no longer follow ordinary rules, where time itself may not yet have separated from space, where quantum uncertainty dominates, where what existed was not yet anything familiar, but also not nothing. It's not silence, it's not chaos. It's just a region of thought where names start to fail. We don't know how long that lasted, if long applies at all. It might not have been a duration in any meaningful sense. It might have been a transition not through time, but into it. A kind of becoming rather than a sequence. And the more we try to describe it, the more we return to approximations. Mathematical constructs, boundary proposals, symmetry conditions, models that don't give us a clear picture but at least give us a frame. Still, something about it draws the mind in. Maybe it's the simplicity, maybe it's the depth, maybe it's just that when you strip away all the structure that followed, the galaxies, the atoms, the forces, you're left with something pure. Not clean in the sense of being tidy, but unprocessed. Not yet shaped by entropy or cooled into separateness. Whatever it was, it's what everything came from. Not in a mythic sense, not as a metaphor, but as the best scientific guess for how the universe began to evolve from conditions we still don't fully understand. The dark before light isn't empty space. It's the boundary between the known and the undefined, between what we can describe and what we can only infer. And drifting into that space, not rushing, not solving, just drifting, is part of how we engage with it. We can follow the data as far back as it goes. We can test models, refine them, discard them, start over. But the earliest state, the very beginning of what would become time, still resists full exposure. It holds its structure close. And instead of trying to tear it open, sometimes it's enough to approach quietly. Because whatever that state was, it gave rise to everything. To the laws, to the space, to the possibility of stars, of water, of memory, of language. We're shaped by it, even now, by that initial condition, by the values it set, by the energy it distributed, by the asymmetries that allowed complexity to develop. But none of that needed to happen. As far as we can tell, the universe didn't have to exist. And if it did, it didn't have to be this one, with these constants, these structures, these directions of time. So when we drift into that darkness, we're not just tracing a scientific history, we're passing through a threshold in thought, a place where explanation softens and awareness expands. It's not about finding something hidden there, it's about sitting quietly in the presence of what may never be fully defined. The early universe didn't announce itself, it didn't explain, it didn't unfold with commentary, it simply moved, expanded, cooled, and here we are, billions of years later, running simulations of what that might have looked like, before photons could travel, before nuclei formed, before clocks could tick. You don't have to solve it. You don't have to build a complete theory of everything to feel the shape of what came before. You can just let it be. A dark, dense, quiet region at the edge of time, not waiting to be illuminated, but already doing what it does, giving rise to structure, to laws, to time, without needing permission. And you, wherever you are, whenever you're hearing this, are still inside the result of that beginning. Still drifting very slowly in the same expansion. Not watching from outside, not interpreting from afar, just part of it. Thanks for spending some time here. If your eyes are heavy now, if your thoughts are slowing, that's okay. These kinds of questions don't need fast answers, they just need space. And maybe that's what this gave you. A little space to wonder without pressure, without needing to know. This is Science for Sleep, where science isn't a lecture, it's something you drift through. Wherever your thoughts are now, whether they're circling stars or settling into stillness, you're exactly where you need to be. We'll be here next time. Sleep well.